Hello folks, today I have a situation of finding the formula for the force experienced by a current carrying conductor in the magnetic field. In previous lectures we have dealt with the reason for the force, so why the force originates when you place a current carrying conductor inside magnetic field. Then we applied left hand rule of Fleming to find the direction under several conditions, 24 possible conditions. But now is the time to find the expression for that force, often called as Lorentz force. So in physics, in most of the cases, what we do is to find the expression, we observe experimentally or empirically on what factors does it depend. So here also it is the same thing. So now this force depends on several factors. The first factor that it depends on is the force depends directly on the magnetic field strength. Magnetic field strength. So why? It's because the more this magnetic field is, there will be more field lines. More field lines means that there is a chance of stronger interaction between these magnetic field lines and these field lines. So more these field lines, they will have more chance of interaction between these and these. So that means the force will be higher. So more the interaction, more will be the difference in the intensities here, higher magnetic field, lower magnetic field, cancellation here, addition here. And so that's why force should be higher. And if there is no magnetic field, here, there can't be any such interactions, no imbalance at all, no disbalance or imbalance. So that's why force will be zero. So force is directly dependent on that magnetic field strength. So next is the force depends directly on the amount of current here, amount of current. It's because its own magnetic field depends on that B. And if we go through the exact formula, the value will be equal to this B due to a straight line conductor is equal to mu naught I by twice pi into the distance, radius, r, or the distance from the wire, where mu naught is the magnetic permeability, a universal constant, often associated with the permittivity and the speed of light in vacuum. So this is the expression. So that's a B is proportional to this thing. So its magnetic field is proportional to this I, and depending on its magnetic field, the interaction depends. So more interaction will happen if this magnetic field is high, less will happen if this thing is less. So that's why B proportional to that I, which causes that circular magnetic fields. Then next dependency is force depends on the length of the conductor. It is because if we have some field lines like this, and if I have this sort of length of conductor, so only 4 lines are crossing. 4 lines crossing means interaction is less. But if I use this length of the conductor, 8 lines will pass. That means more interaction and more chances of these things. So it depends on length as well. Now the next dependency is, the foremost dependency is, the force depends on sine of the angle between this conductor and the magnetic field. Sine of the angle between this conductor and the magnetic field, this conductor. So at this time the conductor is like this, and magnetic field is going like this. So that means it is at angle 90 degrees. But if the conductor is like this, can you create these sort of regions? Can you have these sort of interactions and create these sort of things? Let us see. So if I have conductor staying like this, let us say, if the conductor is staying like this, and if I have magnetic fields like this, these are the magnetic fields. So NS, so here I have got N and S. So this side is N side and this side is S side. In such case, let us say the current is going in this direction. So current is going in this direction and the field lines will be like this. So they will be coming like this and going like this. So like this. This current is going here. So field lines will be like this, coming, and here going. So what I have is, its field lines will be somewhat like this. So they are coming here from this side and they are going from this side. Concentric circles around the wire. So here also it will be going to this side and coming from this side. So now here, so they are coming from this side and going this side. So now here the field lines are directed like this. These are the field lines of this wire. So they are directed like this. Now this line and this line and this line form angle of 90 degrees. So no cancellation. So they interact at 90 degrees and they give some resultant. Similarly here also the lines are coming like this, and these are the lines of the external magnet. So that's again 90 degrees. So no cancellation. So neither cancellation here nor here. Similarly, when it comes like this, so it is like this. They are coming like this. So this and this and this, 90 degrees. No cancellation, no addition in a different manner. So if I go through this whole region, there is nowhere that cancellation happens. So that's why what happens is, if we place conductor like this, no interaction. No interaction means no uneven interaction. That's why there can be no cancellation or no addition. And because of that, we can't have force. So, but here we have force. And the force is maximum at this 90 degrees. Because, so now if I do like this, the interaction happens only within this area. So view is different here. If I place the conductor like this, if like this, interaction happens within this zone. If it is like this, this whole magnetic field will not fall into this conductor. So only this much falls, not this much. This much only fall. If I do like this much only fall there. If I do like this, almost no. So that's why the interaction, according to the way of happening of interaction, what I can say is the angle is crucial here. So zero interaction, maximum interaction. So that is possible only when it depends on sine of the angle between the conductor and the magnetic field. So conductor and the magnetic field. So the angle forms here. Conductor here, magnetic field here. Angle forms here. So we can see from there. So this here, the angle forms somewhere here. So that's why it depends on this sine theta. So this overall gives, so when I combine them overall, F proportional to B into I into L into sine of theta. So in combination, B proportional to B I L sine of theta. So this gives rise to a constant. So it will give us B is equal to some constant K B I L sine of theta. Now when new phenomena are developed, they manipulate the, sorry, I forgot. They manipulate the equation, manipulate the values in such a way that this constant is 1. So F is equal to BIL sine of theta. So this is the expression for the force experienced. Now again the what we talked before comes into existence once again. So if a theta equal to 0 degree, that means conductor here, magnetic field also here. In that case, I will have F equal to BIL sine of 0 equal to 0. If I have theta equal to 90 degrees, just like in these cases, F is equal to BIL sine of 90, that's equal to BIL, which is the maximum possible value. So this is the expression for the Lorentz force experienced by a current carrying conductor, and these are the minimum as well as maximum values. So this is the theoretical consideration, the conceptual things, something which we cannot see, but something we can regard as a concept. So concept is very essential for these things, and these things are not generally given in the books. So they were present in old books, but in new books they are not, because they take it for granted. They think that it should be in your head, what they think is. So ultimately it will be in your heads if it is transferred from my head. So some of my teachers transferred this thing from their head to my head. So that's what has happened here. So this is the expression for that force.